We're going to discuss units in chemistry. The basis of most units in chemistry are the SI units, the System International Units, and there are several of those that are the basis for all other units. They're listed here on this slide. And the first 5 are ones that we will use in this course, and those are mass, length, time, temperature, and amount of substance. So these are the ones that we will use. In addition to the ones we use in this course, there are electric current and luminous intensity. We will not use those at all, but those form the full set of SI units. Okay, when we measure things, masses of things, we measure it in kilograms, which is abbreviated kg. When we measure in length, it's the meter, abbreviated m, small case m. Time is measured in seconds, abbreviated to simple s. Temperature is measured in kelvins, which is a capital K, and the amount of a substance is in moles, abbreviated MOL. You may notice that there is no unit for volume in the SI units, and we'll talk about why that is in a moment. All of these units, and in fact many other types of units, have some prefixes that we use for amounts that are much larger or much smaller than the basic unit. So they have a multiplier. So if the basic unit goes where this dotted line is, any multipliers that are larger are above the line, and any multipliers that are smaller go below the line. So if you have a unit that's, say, a meter, you can apply any of these prefixes to that unit. So these are the ones that are most common. These are not the full set, but these are the ones that we will focus on the most. So if you were talking about meters, you'd put kilo in front of it, and it would be a kilometer, and you would put the abbreviation small k in front of that. So that would be a kilometer, and that's 1,000 meters. If you want a million of something, you use mega, which is 10 to the 6th, or a million times, and that's a capital M. You may have heard of that in terms of several things, including megahertz. And hertz is not an SI unit, but again, these prefixes can be used on other things besides SI units. If you have a billion of something, 10 to the 9th, it's giga, something capital G. An example you may have heard of is gigabytes for sizes of hard drives. All right, going smaller than the unit are the ones listed below this dotted line. We have 0.1 times something, 0.01, 0.001, which is 10 to the minus third. And we also have 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. Again, this is not the complete set, but these are the most common ones. If we're talking about a tenth of something, we put deci in front of it and the abbreviation D. If we have a hundredth of something, we call it centi and use a C. So we could use that in front of, say, grams, and it would be centigrams. 10 to the minus third of something is milli. You have heard of that for many things, but one of them could be millivolts. It could be used in front of volts. 10 to the minus 6 is micro, abbreviated with a Greek letter mu, or sometimes just a U. 10 to the minus 9 is a nano something, and 10 to the minus 12 is pico something. All right, and we use scientific notation many times when we have very large or very small numbers, and you are expected to be familiar with scientific notation. This is simply a quick review of how to get a number in scientific notation. So if we have a number such as 0.00174, we want to put it in scientific notation, we always move the decimal point over to the left or right in order to make a number that is one digit to the left of the decimal point. So we're going to put our 1 to the left of the decimal point and make it 1.74, and then the number of places that we move the decimal point will give us the exponent. So we always put one digit to the left of the decimal. And The exponent will tell you how many decimal places you moved. In order to make that happen. And if you move the decimal point to the right, it becomes a negative exponent. If you move the decimal point to the left, it'll be a positive exponent. All right, let's do an example of using prefixes to convert numbers. If you know that 0.01 meter is 1 centimeter, then you can use that as a conversion in order to convert from either meters to centimeters or centimeters to meters. So let's try this problem, which is converting 241 centimeters to meters. When we do this, we start with the number we're given, 241 centimeters, and you can always put something over 1, so we will do that. Putting it over 1 does nothing. It's dividing it by 1, doesn't change it at all. And then we use this equality as a conversion factor, and what we want to do is get our answer in meters, and we want to get rid of the centimeters. So getting rid of means canceling, and you need to have the one you want to get rid of. If it's on the top here, it needs to be on the bottom for your next factor. So we'll multiply by a ratio of the two equal things, because two equal things over each other is the same as multiplying by 1. So we're going to put 0.01 meters on the top and 1 centimeter on the bottom. Again, the reason is so that we can then cancel the centimeter units and get rid of them, and our answer will be in what's left, which is the meters. Then we can use our calculator to multiply 241 times 0.01, and we will get 2.41, and the unit that's left over is the meter. All right, I want you to try a problem now, and so you can pause the video while you calculate the problem. You need to convert 2.77 Kelvin into millikelvin. Okay, and the way to do that is you take 2.77 Kelvin, the given number, put it over 1, then multiply it by the conversion factor from Kelvin to millikelvin. And again, you want the kelvins to cancel, 1 on top, so you want 1 on the bottom, and the number of millikelvins in 1 Kelvin is 1,000. Now, you could have also used 1 millikelvin and 0.001 kelvins on the bottom. Okay, you could use that. That's the exact same thing. They're equal. All right, and your answer will be, when you multiply it, 2770 millikelvin. Okay, mass versus weight. What is the difference between mass and weight? We often use them interchangeably, but it's important to know what the real difference is. Mass measures how much matter you have. And it is measured in grams or kilograms. Okay, weight is really just a measure of the gravitational pull, which is proportional to mass for a given location. For instance, on Earth. So on Earth, we have a certain gravitational pull, and that is proportional to the mass. But if you go to the moon, the weight of something would be different, even though it's mass. How much matter there is would be the same. So if you take a ball and measure its mass on Earth and its weight on Earth, and then go to the moon, or Jupiter, or anywhere else where there's a different gravitational pull, you will find it has a different weight, but it still has the same mass. All right, and we measure weight in things like pounds or newtons. All right, and I said I would get back to volume. Why wasn't there volume in the list of SI units? The reason is because volume is actually derived from one of the basic units. It is derived from length, which we measure in the meter. but volume is generally measured in liters. Okay, so what is a liter and how does it compare to a meter? Well, it turns out that 1 liter is this unit. This is 1 liter, and that is equal to a decimeter cubed. So it's 1 decimeter deep, 1 decimeter tall, and 1 decimeter wide, and that is 1 liter. And 1 centimeter, a little cube out of that, 1 centimeter cubed is the same thing as 1 milliliter. And that conversion is an important one to keep in mind. Okay, now that we understand mass and volume, we can talk about density. All right, and so we're going to talk about it in terms of a sponge. Density is the mass of something divided by its volume. Okay, the mass is in the numerator, volume is in the denominator. And the units are frequently something like grams per milliliter. All right, so let's look at our sponge and talk about some changes that we could do to the sponge. All right, the first change we're going to do to our sponge. So the sponge has some density, it has some mass and some volume, and what are some changes we can do to the sponge? Okay, first thing we can do is squeeze it. Okay, what's changed when we squeeze it? The mass, the volume, both. Okay, which one has changed? The mass isn't the same, isn't different, has not changed. It still has the same number of molecules of matter in it, so it still has the same mass. What's changed when you squeeze it is the volume. Okay, so the volume went down. Okay, what happens to the density if the volume goes down? The volume is in the denominator of the density equation. So when a number in the denominator goes down, that means the density will go up. So density goes up, it gets more dense. That makes sense. You squeeze a sponge, it's more thick, it's more dense. All right, let's try another change. What if we pour a little bit of water into the sponge, make it a little more full of a little more mass? Okay, so what I just gave it away. What's changed? The volume of the sponge hasn't changed, but the mass has changed. How has the mass changed? Greater or less? The mass has gone up, right? It's gotten bigger. What happens to the density? Well, the mass and the density, the mass is in the numerator, and so the mass and density are proportional to one another, so the density will also go up if you pour water in it. All right, let's do one more change to the sponge. Let's cut it in half, and then we'll only consider 1/2 of it. Okay, what have we changed? Mass or volume or both? Well, it turns out we've cut the amount of molecules in half, so the mass has gone down. And what about the volume? We've cut it in half. The volume has also gone down. And what's important to note is the mass and volume have gone down by the same factor. Okay, they each become 1/2 of the original values. So what happens to the density? The density isn't going to change at all. You've lowered the numerator and you've lowered the denominator by the same factor, so the density remains unchanged. All right, let's do a calculation based on density now. I want you to try this. Be sure to stop the video so you can try to calculate it. Calculate the density of a liquid substance if a 25 milliliter flask holds 17.3 grams of it. Okay, so how do we solve this? Remember that density equals mass over volume. All right, so the mass is given 17.3 grams. Mass is measured in grams. The volume is given in milliliters, 25.0 milliliters. Use your calculator. 17.3 divided by 25.0, you get 0.692 and the units are grams per milliliter. Milliliters is still in the denominator. Okay, next let's talk about how temperature and heat compare to each other. They're very similar, but they are definitely different things. Temperature is a measure of how hot something is. And heat is a form of energy. Now, if you add heat to something, you will often change its temperature, but they are not the same thing. All right, so we said that we measure temperature in units of kelvins, which is the SI unit, but in chemistry we frequently also use Celsius, degrees C. Now notice that kelvins does not have a degree symbol before it. Celsius does, kelvins does not. And we can convert between kelvins and Celsius. Kelvins are equal to the number in degrees Celsius plus 273.15. So that is the conversion. And occasionally we also use the units Fahrenheit, although we rarely use it in science. But the conversions between degrees Celsius and Fahrenheit are given here. This equation starts with degrees Fahrenheit and converts to Celsius. This one starts in Fahrenheit, or Celsius, and converts to Fahrenheit. All right, but let's just look at the three different scales then, Kelvin, Celsius, and Fahrenheit, in terms of something we're very familiar with, which is water, and where it has phase transitions of going from solid to liquid and liquid to gas, also known as melting and boiling. All right, so in the Fahrenheit scale, water freezes or melts, either way, at 32 degrees Fahrenheit, and water boils at 212 degrees Fahrenheit. And the difference between the two is 180 degrees Fahrenheit. All right, but in Celsius, which is based on water, water freezes at 0 degrees, very easy number to remember, and it boils at 100. Really nice scale based on water and where it boils and freezes. Okay, now notice this is very different. This has a gap of 100 degrees, whereas Fahrenheit had a gap of 180 degrees for the same difference. So every degree in Celsius is larger than every degree in Fahrenheit. All right, kelvins though. Kelvins are related to degrees Celsius. It's just a term that's added. So kelvins starts at freezing water. It's already up to 273 degrees Kelvin. Absolute zero is way the heck down. Below, way below this scale. We're already at 273, but when you get to boiling water, it's 373. You simply add 100. So the difference between boiling and freezing for Kelvin and Celsius are the same. They have the same gap between them. Okay, and our final topic for this segment is on precision and accuracy. Okay, what is the difference between numbers that are precise and numbers that are accurate? You are going to be doing a lab that talks about this also. Precision is a measure of how close different values are to each other. And I'll give an example in a minute. Accuracy is a measure of how close values are to the correct answer, not just each other. Okay, so values are close to the right answer if they're accurate. The right answer. Okay, and you don't always know the right answer, but let's say sometimes you do. All right, so I'm going to illustrate this with a field of cattle. Now let's pretend that we have a little car. Okay, you're going to laugh at my drawing, but we have a little car, and there's people in it. People driving along, and they drive by this field of cattle. Okay, and then somebody says, hey, how many cows were in that field? Okay, so the car is full of 3 people, and let's say everybody says what they think for the count of the cows in the field. And they drove by too fast to count accurately, but they did their best. Okay, so one person says there's 15 cows. Another person says, yeah, there's 15 cows. And another person says there's 16 cows. All right, those numbers are pretty close to one another. You would say that they are precise. They agree with each other. The three people in the car agree with each other, so their answers are precise. All right, this is going to be car number 1. However, if you start counting those cows, you'll find out that they are not all that accurate. All right, so let's say car number 2 drives by, and they say, one person says 25, another person says 30, another person says 20. Okay, the right answer is actually 25. So this car was pretty accurate. The average of those three is right on the right answer. Okay, the average of those three is 25, which is the right answer. So this is an accurate group. But they're not very precise because they didn't agree with each other. Okay, so that's car number 2. And now we'll have a third car go by, car number 3. And let's say that there's 3 people in that car too, and they say, one person says 25, one person says 24, and the third person says 25. Okay, they're pretty close to the right answer, and they're pretty close to each other. We would say this car is accurate and precise. So there's an illustration of accuracy and precision.